Hello viewers, so we have this question that says find the percent ionization of a 0.250 molar formic acid solution. So we're given, say we have a 0.250 molar um, formic acid solution and we are looking for the percent ionization. So let's go ahead and work out for that. Now, what we have here is formic acid. So the first step is we're going to show the dissociation of formic acid, or rather write the dissociation equation. So the dissociation equation will be the formic acid, when you put it in water, what you're going to produce on the other side, you have the hydronium ion and the conjugate base. So this is what you have when you write your dissociation. So the next step is to have our ice table. So we'll say our ice table here, where we are saying the initial concentration we have for the acid is 0.250. So we have 0.250 for the acid. Water is not included on the ice table, so this part here is not going to be involved. It's in liquid form. Then we have 0 here, and we have a 0 on the other part, like that. Since we have 0.250 here, we have something on the left-hand side, and we don't have anything on the right-hand side. The chemical reaction will proceed to the right side. That implies to say the left side is going to reduce, and the right side is going to increase. So what we are saying is this will reduce by a certain amount that we are calling x. So on the change, we'll have minus x. Then we'll have plus x there. We'll also have a plus x here. Then we'll have 0.250 minus x at equilibrium. Here we're going to have x, and we're having x on that part too. All right. So after that, our next part is to write our Ka expression. So Ka will be equal to the concentration of the hydronium ion that we have there multiplied by the concentration of the conjugate base. This will divide by the concentration of the acid. So that's what we have there. All right, so after that stage, we're going to now replace with what we have at equilibrium. So our Ka for formic acid is a value that you should know. The standard value is 1.8 times 10 to minus 4. And this will be equal to what we have on hydronium ion, and the other part, the conjugate base, is x, and x at equilibrium. Then down there we have 0.250 minus x. So that's what we get when we replace. So we are going to have 1.8 times 10 to the power of minus 4, like that, is equal to, on top there is just x squared. Now down here, we're going to ignore this x. We're ignoring it with the concept of the change. This value of x is very small, that the change is going to bring to the initial concentration is very small, that it's not going to affect anything, and is below 5%. So the change in this concentration will be below 5%. So that's an assumption we are making, and we are going to check if it's correct or not. Yeah, so let's do that. So what we have is we're going to have 0.250 down there. And this implies to say our x squared now will be equal to, when we cross multiply, we're just having 1.8 times 10 to minus 4 there. This is multiplying by 0.250. We cross multiply like that. So this means our x now will be equal to the square root of what we get there. So in short, the square root of 1.8 times 10 to minus 4 like that, multiplied by 0.250, like that. Our X value will be equal to, according to what I'm finding here, I have 6.71 times 10 to the power of minus 3 molar concentration. So this is the value of X, and the value of X is the same value for the hydronium ion concentration. You see this X here is the same value for the hydronium ion concentration at equilibrium. So the value we found here is also the concentration of the hydronium. All right, so let's proceed and see how we can get the percentage ionization. So percent ionization is equal to the concentration of the hydronium ion. So the concentration of the hydronium ion divided by the concentration of the acid. So the acid we have is HCOOH concentration, and this will multiply by 100%. So this is equal to, we found the hydronium ion concentration to be 6.71 times 10 to the power of minus 3 molar concentration. This is dividing by 0.250, which is the concentration of the acid, and this whole thing must multiply by 100%. When we do our mathematics there, according to what I'm getting here, I have 2.68%. So this is the percentage ionization. And you can see that the percentage ionization is less than 5%. So our assumption of ignoring the X earlier on here, ignoring this X at this stage is okay because our percentage ionization is less than 5%.